True. So CO2 emissions can cause ocean acidification, okay? And ultimately what's happening is that CO2, or carbon dioxide gas, reacts with water. And in the process reacting with water, it can produce products. The products of those reactions are acids, which is why our ocean gets acidified by putting too much CO2 into the air. Okay? There's a fine balance that we would have to play with. That fine balance is also the fine balance that is found within your bloodstream. Okay? We monitor or deal with the pH of our blood very much the same way as carbon dioxide acidifies the ocean. So what are some examples of everyday substances that are acids or bases that you know of? We've got our blue box. Since no one's been excited about talking, maybe you'll talk better at your tables about a straightforward question. Maybe. So in theory, we've seen a variety of different things. We've learned some new stuff. If you hadn't heard about it, pink stuff is apparently a cleaner that is basic. Okay? And if we go through and look at these, we've got a lot of juices on our acid side, and then we've got a lot of soaps and cleaning materials on the base side. Ultimately, they're both doing something very similar. We'll get back to that. They're both playing around with hydrogen ions. Okay? And as we navigate the locations of different hydrogen ions, it can change the physical properties. Okay? By changing those physical properties, it can leverage certain actions to go through and happen. Okay? So for acids, we might say, oh, well, it helps to dissolve things. So if you put like a tooth in like soda, what eventually happens to the tooth? It decays and dissolves away. If you haven't seen that, it's kind of interesting and scary at the same time. Okay? So don't mouthwash with soda, I guess. And then our soaps are going to go through, and they are also going to react and play around with hydrogen ions, and by changing those hydrogen ion concentrations, they will go through and change those individual properties and start to dissolve things. Okay? So what is specifically happening? An acid is a molecule that loses H plus when it reacts with water. Okay? The loses H plus is a standard definition, particularly for Gen Chem. I would argue we look at it as an H plus donor. If we were going to spin around and look at it at organic chemistry, not a big deal, but just something I would go through and say. Okay? So if we look at a standard acid, we have an example of hydrochloric acid. The overall reaction that we're showing up at top is our blanket form. We have HA. Why do we pick A? Acid begins with A. We're not very clever. Okay, so that's a good description for our acid. If we go through and look at it reacting with water, okay, ultimately the reaction with water is now an Arrhenius definition. Okay, we're going to produce A minus and H3O plus. Okay, so that's the H plus process through this. Okay. Why does the water become positively charged? We go through and look at this. H3O plus. It's now positive, right? Why? A proton. Okay. What are you talking about a proton? What are you talking about when you say proton? Okay, sodium. Does sodium have a proton? So if I just put a sodium on it and did sodium chloride, that's now a cation? Huh. Why is it becoming positive? And saying proton isn't a bad statement. It is very commonly used, and we'll come back to why we would call it a proton. Okay. If we're talking about an H plus donor, HA is giving up H plus. Water was what charge? Water was negative? How do we know it was neutral? How do we know what its charge is? What charge is HCl?
It's neutral.
What charge is carbonate?
Negative.
You can do better. What charge is chloride? -1. Okay. How do you know what the charge is? It's specified in the upper right-hand corner. Okay? That's what Gen Chem was teaching you when we talk about atomic theory, is looking at where those charges are. Once we've now moved beyond that, guess what? The charge is always going to be given to you in that upper right-hand corner. So if we go through and run a chemical reaction between HA and H2O, both of them are neutral. We know they are neutral because in the upper right-hand corner, there's nothing written. So they are by definition neutral. Okay? Why should the charge change when I run the reaction? Well, that's going to have to do with the chemical identity of what's moving around. Well, what's moving around? Do better. It's not just hydrogen. It's hydrogen ion. Okay? It's the cation. Okay? It's H+. So if I look at HA and I remove H, what should my symbol be? If I remove H from HA, what's my symbol? Easier than that. A. That's it. It just becomes A. I'm not removing just H. I'm removing H+, which means my symbol must become A-. If we look at what happens to the water, okay, water was neutral. What did it do? It added an H, which means it becomes H3O. We have an extra hydrogen on it. Why? What would its charge then become? Positive, because it was a hydrogen that was positive to begin with. So what you're trying to do is break down all of those individual symbols into those representations. So if we looked at an example of hydrochloric acid reacting with water, what should it produce? Okay, Cl- and H3O+. Did I do what you said? What?
Does it matter if you put the Cl first or not?
That's a good question. So did I do exactly what you said? No, I swapped the order. Does the order matter? No, this hopefully isn't a think anymore. This should be 151. The order doesn't matter in which you place those. Does that make sense? Okay. So that's what an acid is. Reacts with water, produces H3O+ and Cl-. Okay? At least as far as you're concerned within this class. Okay? What is a base? Again, according to our definition from Gen Chem, it gains an H+. Okay? Subtle change, it's an H+ acceptor if we were going to talk in organic chemistry language. Okay? So we could look at an example reaction. Why don't we look at the reaction we just looked at first? Didn't I have HCl? Oh, I know why. Never mind. Well, not never mind. We're going to do it. Why don't I look at this reaction? Can I describe the action of a base with this reaction? HCl was what? An acid. What do acids react with? Bases. What did the HCl react with in this case? Don't tell me a base. What did the HCl react with? Water. Guess what water is acting as? Okay. This gets a little bit weird with this definition because according to the definition, a base is a molecule that gains H+ when it reacts with water. In this case, water's the thing that's reacting. Okay. What is it doing? It's accepting the hydrogen. Why this weird reacts with water? Why is that part of our definition? So a couple relatively straightforward explanations for this. Do I need to include the when it reacts with water? No. Then why do we include it? Everybody's favorite subject. history. Okay? When we look at the reactivity of acids and bases, we're talking about them where they historically came from. This definition is a slight permutation off of the Arrhenius definition of acids and bases, which is looking at how things respond when they're mixed with water. Okay? That's it. It's a very narrow definition, but why would we use that definition today if it's such a narrow definition? Is water's sole role in this reaction to act as a base? No, it's not. What's its other role? Said potentially another way, if we go back and think about what we had to go through and do in Gen Chem with our chemical reactions, we probably had to add some more information to our chemical reaction. What other things did we have to add to our chemical reaction? Give you a hint. What did I just add to the chemical reaction? The state of matter. What's the state of matter for HCl? What does aqueous mean? Dissolved in water. What's the role of water? It's the solvent. So the water is acting both as a base and as a solvent. When we're talking about our acid-base definitions, why would we worry about water reacting as a solvent? What do you exhale? Carbon dioxide and water. What's in your bloodstream? Don't tell me blood. Water. What are you drinking? Water. What's in your food? Water. What makes up, well, I don't know the number, 70 to 80% of the planet? Water. Water is everywhere. So when we go through and talk about chemistry, when we're looking at those chemical reactions, what we're concerned about is the primary solvent that we would deal with and interact with. Water is everywhere. When we talk about this definition, Arrhenius is a very old, long dead dude. Okay? Why did he look at water first? Because that was the solvent that he had to work with. Okay? So when we're manipulating these things, almost everything we do is in water, which means when you navigate through all of your chemical reactions, guess what phase you're going to be in? Water, which means your phase will be aqueous. Okay? If we switch it up to the hardcore definition, okay, a base is a molecule that gains H+ when it reacts with water. Okay, is again a permutation of that definition. But what we're looking at is this base molecule with a symbol of B, because base begins with B. So we're slowly waking up. Right? The base reacts with the water to accept an H+, to gain an H+, which means if B gains an H+, what happens to it? Well, what's going to change about the symbol? What do I need to write next to it? An H. Okay, I don't want to write H+ because now I'm inserting a charge into the middle of my formula. Okay, where do I want to put that plus? At the end of the formula, and we get BH+. Okay, that charge is always getting written at the end, upper right-hand corner of our system. Where did the H+ come from? The H2O. Okay? So H2O loses a hydrogen. If it has lost a hydrogen, what happens to its formula? Decrease in H. That's a good statement, which means we only have one hydrogen there. What charge was that hydrogen we lost? What charge is the hydrogen that we lost? Positive, which means the resulting structure needs to be negative. That's where our charges are manipulating and allowing us to manage our way through this. Okay? That's our basic pattern for a base. Get it? I said basic pattern. Okay. So, do NH3. Your turn. NH3 acts as a base. Draw out your chemical reaction. So what happens? NH3 plus H2O. What does the NH3 do? What?
I thought you said that NH3 was the base.
Oh, I did. Did I not just say that again? What, I just said what happens, right? NH3 plus H2O. Did I say something else? No, I'm panicked. Okay. What happens to NH3? If it acts as the base, I get NH. Now 4, we have to add that hydrogen, but the hydrogen that we accepted was positively charged. Since I started neutral, that needs to be positive. What else is remaining? NOH negative. Yes?
So why isn't H2O base this one? Because it was a base. What changes is NH3 as a base?
So it's a really good question, and probably because it wasn't picked up within the recording, let's state it again. Okay? We just walked through and said H2O was acting as a base. And now what are we saying the H2O is acting as? If we go through and look at what changed to the H2O, what happened? It lost H+. And if it lost H+, that sounds an awful lot like an acid. But didn't we just say H2O was a base? Yeah. Why is it changing?
Is it because it's neutral?
It's going to come back to that. Say that again.
Ammonia is more basic than water.
It has to do with what it's reacting with. So water's ability to act as an acid or a base, and we'll push that even further, every species' ability to act as an acid or a base is dictated based off of, not intentional, okay, what it's reacting with. Water has an interesting property because water is our default solvent everywhere. We can look at it as the dead center, which means if I throw something more basic at it, what happens? Water's going to act as an acid. If I throw something more acidic at it, what's going to happen? Water's going to act as a base. And it's going to pick and choose effectively what chemistry it's going to run. If we go through and look at NH3, could NH3 act as an acid? Well, what did an acid need to do? What did an acid need to do? Lose an H+. To lose an H+, what must it have? It has to have an H. Does NH3 have an H?
Yes.
Could NH3 act as an acid? Yes. But it doesn't in this particular scenario. Okay? That's now going to come down to trying to rank acid and base strength, which I think we're going to save for a little bit later today. I'm a little nervous about context on that because I didn't see anything stand out to me that I would have talked about. So we'll see what happens. Okay, so we'll have to come back to that kind of deciding which one's stronger or weaker, and we will see it to a certain extent with one of our slides. It just doesn't go into as much detail. So if we go through and look at an acid loses a proton, a base gains a proton. Why is H+ called a proton? Well, what is H? Whoop, that's not what I wanted. What is H? Quite literally, it's hydrogen. Cool, thank you. What makes something hydrogen? One proton, one electron. That's what makes an atom hydrogen. That's how we know it's hydrogen. It has a proton and it has an electron. Okay? If we talk about H+, what did we do? We get rid of the electron, which means what's the only thing floating around? A proton. So when we talk about acid-base chemistry, we can often refer to it as a transfer of a proton because that's all that's actually there. Okay? This can be very misleading because where do protons exist? In the nucleus. Are we talking about nuclear chemistry? No. So this isn't the ability for an atom to absorb a proton into its nucleus. That's not happening at all. All we're saying is that a proton from hydrogen comes nearby and will hang out next to that other atom. in a distance between the nuclei that matches a bond between a hydrogen and whatever the other atom is. Kind of makes sense? Right? I do want to mention this mainly because I'm getting this question in organic chemistry because it shows up every so often. If we look at the symbol or the notation for the most common isotope of hydrogen, it's H1. Note the 1 is in the upper left-hand corner. What shows up in the upper left-hand corner? Actually not the number of protons. The number of protons shows up in the lower left-hand corner. What shows up in the upper left-hand corner? Electrons are dealing with charge, and the electrons are ultimately being represented in the upper right-hand corner. Upper left-hand corner. What's in the upper left-hand corner? We'll give you another hint. This is the one that's been stumping students right and left. What the hell element is D or 2D? What is this? Okay, deuterium, which is a good statement. Yes, it's deuterium. Okay, and if we add some more information to it, because if we're looking for element D on the periodic table, we're going to have a really hard time because it's not on the periodic table. Okay? Let's go ahead and put the atomic number, our number of protons, in the lower left-hand corner. Say again?
Is it them added together?
What's them?
Protons and electrons.
No,
It's not the protons and electrons.
Protons and neutrons.
It's the protons and neutrons. Upper left-hand corner was your mass number. It's the protons plus the neutrons. When we look at hydrogen, or hydrogen 1, the most common isotope, it has no neutrons. Why does it not need a neutron? Why do we have neutrons?
To balance out.
Right idea. Balance out the protons. What do you mean by balance out the protons? What happens when I bring two positive things near each other?
Get one repels.
They repel away, so we need the neutrons to come in. Why does hydrogen not need a neutron? There's no other protons. Okay? Could it have a neutron? Yeah, just like every isotope can have differing amounts of neutrons. The isotope is dictated based off the neutrons. So when we talk about hydrogen, we can look at the element deuterium, which is really just heavy hydrogen. You've added an extra neutron to it. Is that going to change its chemistry? Most of the chemistry is dictated based off of the protons and ultimately the electrons. Are those changing? No, all you're changing is the mass. Okay? So deuterium has very little effect on the overall chemistry of hydrogen. We can just detect it and we can see that. Kind of, sort of? Cool. So, the next thing we want to do is address this idea of conjugates. Okay? And why might we want to address the idea of conjugates? Well, we just spent 4 weeks, right, looking at chemical reactions. And if we look at this chemical reaction, what chemical reaction am I trying to describe? What do you think HA is going to act as? An acid. Why? It's A. Cool. What am I going to produce? H3O positive and A minus. Okay. We spent 4 weeks talking about what? Two answers you could use, but the most recent 4 weeks. Equilibrium. And what was equilibrium talking about? What'd you say? Reverse reaction. To go from H3O plus to H2O, what did I do? What happened to it? It lost an H. And if it loses an H, what is it? Ah, it's an acid. But I thought HA was the acid. What did we say H2O was? A base. What is A minus acting as? To go from A minus, all the way to HA, it had to gain an H positive, which means it's acting as a base, which is going to introduce a dilemma. If we now back off some of that information Yep. Which species is the acid? That's now really confusing because I don't know which species is the acid because I have two acids depending on which way I'm talking about the chemical reaction running. Which means what do I need to do? I need to introduce some more language so that I can understand which thing is which. Okay? When we're talking about our acids and bases, almost universally our acids and bases are defined on the left-hand side of the arrow because the left-hand side of our arrow are the reactants. So I need something to distinguish the acids and bases on the right-hand side of the arrow. So I need to change the name of those. How do I change the name of those? It's on the board. It's the very first word. That's a conjugate acid and the conjugate base. I can go through and also reference conjugate acid-base pairs. What are we talking about within those pairs? H2O is the base of H3O+. Okay? The conjugate acid-base pair is H3O+ and H2O. The conjugate acid-base pair for HA, whoops, come on, pen, is HA and A-. Those are conjugate acid-base pairs. Kind of, sort of? It's just a language simplification, which sets us up with the next question. I want you to go through and do this exact same thing, but now, instead of using HA and water, I want you to go through and use formic acid. Formic acid gets a little bit trickier because we've got a Lewis structure drawn, so you've got to manipulate your Lewis structure. Decide whether you think it's going to act as an acid or a base. Run the chemical reaction you see fit. The formula of COOH with a minus, or do I end up with the formula of H, started to write the same thing again, HCOO minus. Okay. In both cases, what are we having it act as? An acid. Okay, so the product is still coming out as H3O+. How do we know it's acting as an acid is a very valid question that gets a little bit beyond the full scope of what you're trying to do here, but we do have a little bit of an answer in that. How do we know it's acting as an acid? It's called formic acid. Okay, use the name to leverage your help to deciding that that's acting as an acid. You can absolutely discover that it acts as an acid different ways, okay? But that, I think, again, is beyond the scope of what we want to look at. So which formula is correct? How are those formulas different? Which is carbon dioxide? Why is the one on the right not carbon dioxide? Does it contain different information? What information is it containing? Say it again. Does the order matter? Okay, let's try a different one. H2O versus HOH. Different substance? Is one more correct than the other? Both are equally valid. And it's all going to depend on the context on which you're going through and using it and what you're trying to represent as you navigate it. So how are these two formulas actually different from each other?
I think those are different because one's saying that it's bonding with an oxygen and a hydrogen, the other one's saying it's bonding with hydrogen with
And this becomes the challenge within that. Okay, if you're going to go through and say that, when I look at water, is the structure HHO?
Yeah, it's different.
When I look at H2O, when I write the formula H2O, we think it means HHO?
No.
No. So what does that suggest about our formulas? Complete and utter trash. Particularly if you're given the context of what the flippin' structure is, Don't remove information, keep the information. So when we're going through and looking at COOH minus versus HCOO, I already forgot what it was. What we're talking about is something along these lines, which is exactly what you're trying to get at, but your structure or your formula doesn't provide that context. What you would need would be the Lewis drawing. We're going to come back a little bit. Have I appropriately drawn the products? Okay. What did we say the top one was formula-wise? COOH. That's all we said it was? Ooh, minus. What did we say the bottom one was? HCOO minus. Does that red structure show a minus? Does the purple structure? Those are supposed to represent those formulas. Something's missing. What's missing? Say that again, a little louder for me.
Brackets with the charge.
We could try brackets with the charge. We don't even need to do that. We can actually get more specific, which is pushing into OChem. What did you remove from this structure to get the red structure? You removed the hydrogen with how many electrons?
0.
0, because it was H positive. What happened to those 2 electrons? Because that's a line, right? That line represents 2 electrons. Where are they?
Just a long bit.
A lone pair on the carbon. Where are they in the purple structure?
They can't go. They'd have to be on the oxygen.
They'd have to be on the oxygen. So if we're now trying to decide between these two, which one is better or more acidic, what do I need to consider? Which atom is going to hold those electrons better, the carbon or the oxygen? And how would I evaluate that? What about periodic table?
Where it's at on the periodic.
Where it's at on the periodic table. Cool. What about where it's at on the periodic table?
Depending on the size of electrons.
What'd you say?
How many bonds it can form?
How many bonds it can form? They both form different bonds, though, so I don't know where that's going to take you. What'd you say? Valence electrons ultimately isn't going to matter.
Electronegativity.
Say that a little bit louder.
Electronegativity.
Electronegativity. What we're talking about is the ability for an individual atom to hold on to bonding electrons. So if we're now evaluating between these two structures, which one is better at holding the bonding electrons, the carbon or the hydrogen? Sorry, carbon or what's the other atom? Oxygen. The oxygen, which means this is the reaction that runs, this top one doesn't. To come up with that prediction, what you're manipulating is what you already understood from 151, electronegativity. And we can go through and look at different hydrogens in a molecule and decide which one is more acidic based off of looking at the product. What's the name of this product, this purple product here? We never learned OChem. You learned it on this slide. We learned how to name that structure. As a hint, if we spin this reaction the other direction, what did it act as? What does my purple structure act as? To go back? It accepts a hydrogen, which means it's acting as a base. But bases, acids and bases, should really only be kept on the left-hand side of the reaction. We're on the right-hand side of the reaction, which means it's the conjugate base. So I can now look at formic acid and I can say its conjugate base is this structure. I could also go to the chemical formula. Depending on the question that's being asked, it's going to change my perspective on what's going on within it. This question very clearly gave us Lewis structures, which means what do we need to be considering? Lewis structures. That's how it works. Okay? Do you always have to worry about that? Nope. Shall we see another example? Of course. Why not? H2SO4 is known as sulfuric acid, which means how is it going to react? As an acid, which means if I was going to ask a question about the product of this chemical reaction, what am I going to ask for? Ooh, real challenging question. If I know sulfuric acid is going to act as an acid, what thing am I going to ask for? Do you think I would be asking for H3O+?
No,
Why not?
because you look for the conjugate.
Just answered all the question at once. I'm not going to be asking for the structure of H3O+, because we already defined it as an acid. And what do acids do? Give up a hydrogen to water, which means they're going to produce H3O+. That's not an interesting structure, because guess what acids produce those? All of them. What's the thing that's going to be different? The base. The base is water. Not on the other side. What I'm going to be asking for is what is the conjugate base? Okay? In this case, do I care where the hydrogen is? No, why not? Did I give you a Lewis structure? No. So all you care about is that I have hydrogen there. One of those hydrogens is acidic, which means I'm going to get HSO4. I lose a hydrogen and I get a negative charge. Does that kind of make sense? Give me the conjugate acid for the hydrogen carbonate ion. Started some conversation. I think we're waking up. That's cool. Okay. If I'm looking for the conjugate acid, what must HCO3 minus act as? It must be acting as a base. Which means what is the H2O acting as? An acid. To act as a base, what must it do? It must gain a hydrogen, right? Which means my formula becomes H2CO3. We're adding an extra hydrogen to it. But it started negatively charged. Why is it neutral? You added a positive charge of the hydrogen, which means our structure becomes neutral. What happened to our water? It lost a hydrogen, so it becomes OH negative, and we now have the conjugate base. Yeah? That's fun stuff. I would love to keep talking about this. Okay? But unfortunately, I don't think I get to. Okay? One of the things that you should be pulling from this slide is understanding what our conjugate acid-base partners are. Recognize that your charges will change. You're not always producing, okay, a charged species in each of your chemical reactions because it's going to depend on the charge state of your initial structures. Those are going to dictate how things act at the end. Okay? If we look at HCO3, hydrogen carbonate ion, we're saying it's acting as a base. Could it act as something else? Yeah, it could also act as an acid. Okay, you asked the question about water. Guess what? Hydrogen carbonate, similar species, can act as both an acid and a base. How would we dictate it? That depends on the context of what your current system is. Kind of, sort of? Okay. So, reaction between acid and water. Here we go. Predict the products of the acid-base reaction and label your acid, base, conjugate acid, and conjugate base. This one should be a relatively straightforward, fast question because you just did it with a much harder question. If we run this chemical reaction in theory, the class should be able to get both of these potential answers. Is everybody okay with that? Okay. Which one is correct? Ooh, the top one. Why is the top one correct and not the bottom one?
Because this says between acid and water, and the first one's acting acid, it's the HCN.
Acid and water. I totally didn't see that.
HCN.
Didn't see that at all. Helps to read the directions, apparently. Yeah, it says a reaction between acid and water, okay, which means water is already defined, which means our HCN must be an acid. So if we're looking at our two chemical reactions, where is HCN acting as an acid? It's acting only as an acid in the top case, okay, not the bottom case. How would you know if we deleted that? You continued to talk, but I got stuck behind it saying it was an acid. What's that?
I'd give up.
I give up. Okay, that's fair. Okay, how do we know which one's which? We don't know at this state. Okay, what we would need is some extra context to help us out with this. Okay, that extra context in this particular unit is going to come into play because what we're going to talk about is looking at these reactions in the reverse. We're looking at them in equilibrium reactions. And if I looked at the equilibrium for HCN, I would probably see a Ka provided to me. Why would I see a Ka? Someone said it. A stands for acid. If you're seeing that Ka, guess what? Our HCN has to be acting as an acid. That's the context. If you see a Kb, now you're talking about it acting as a base. That can get a little bit tricky and a little bit wonky, so what we'll try to do within these particular scenarios is always provide the context of it reacting with it as an acid or a base. Okay, stated clearly in the question. Make sense? How are we feeling? Okay. Okay, which, I know, I should pay more attention to the clock. Okay, takes us to this side. Okay, if we went through and looked at, say, our chemical reactions, back here, this one we said was an acid, so I'm just going to write it out as acid, gives us H3O plus and Cn minus, right? For the formic acid, HCOOH, kills me to write that formula, we also said it acted as an acid. How do I know which of these acids to be more concerned about? Well, what's the thing that makes acids dangerous?
It dissolves.
Say again?
It dissolves.
It dissolves by doing what? Breaking the bonds by doing what? What's the definition of an acid? Loses the H positive. So what is it doing? It's putting an H positive onto your structure, and that causes all these nasty side effects. So what's the primary thing we're concerned about? The H positive. If I produce H positive, that's dangerous. But since we know these are equilibrium reactions, if we tweak this and we say this reverse reaction is very prevalent, but this forward reaction is prevalent, what does that mean? This bottom one produces lots of H+. What is the top one? Not very much. Which one's the more dangerous acid? The bottom one, because it's producing more H+. So if we go through and consider the dangers associated with our acids, it's the ability to give us that H+. That's the danger. Okay? And that's dangerous in high concentrations. Concentration makes the poison. Okay? So if I have lots of H+, that's a very dangerous thing. How do we measure concentrations? Molarity, moles per liter, right? When did you learn about moles? 151, so last week. Okay? But if I go through and tell little Timmy, watch out, that solution has a high concentration of H+, what the hell does that mean? Okay? I could push and say, well, it has a high molarity. There's moles per liter. Does this little Timmy know anything about moles? No one's saying Tim, right? Okay, good. Let's check. Okay? That's going to be really hard for him to understand. particularly if we even push to the powers of 10 and exponents and all of those nasty things. So what did scientists go through and do? They created the pH scale. The pH scale is a way to modify our understanding and remove this concentration aspect from it and turn it into a numerical scale conveniently between 1 and 14. Right? Why is it special to have 1 and 14 and not these weird powers of 10? How well do we know powers of 10? Not very well. How well do our little kids know anything about 1 to 14? They know that pretty well because fingers and toes, they can count it out. There it is. Right? So if we can create a scale that allows us to understand something about reactivity, this scale can now simplify our understanding and spin it into numbers between 1 and 14, and that makes life easier for the general public. That's the point of pH. How do we get pH? Negative log. So we take a number that nobody understands, doing a mathematical manipulation, I'm just going to say it, that nobody understands, to turn it into a system that now everybody can manipulate and understand. That's the point of our pH scale. The pH scale is neat because it gives us information both on the acidic side, battery acid, don't stick your hands in the battery, versus drain cleaner, don't stick your hands in the drain cleaner, versus dead in the middle, 7, water, that's okay, you should use that more often to shower. Okay? Kind of make sense? Our pH scale gives us that information, but in a coded way. What does that mean you're going to have to do now that you've grown up to become chemists instead of being little Timmy? Yeah, you have to decode it. You're going to have to decode that pH scale into the concentration scale that we've been manipulating and working with. Oh, that clock is horrible. Kind of, sort of? There's a decent place to stop.